All right. Well, I want to thank the Watershed Council and Friends of Cape Falcon Marine Reserve for inviting me to give me this chance to share with you some of our work on ocean changes in Oregon. And I'm going to do two things tonight. First is I'm going to show a video about ocean acidification in Oregon. And we do this because, as a scientist, sometimes it's not that easy for me to really clearly convey what's really important about an issue. And certainly it's hard for me to convey kind of the diversity of voices around issues as big as ocean changes. We have an incredibly productive ocean. When we go out there and do our research, when I'm waiting for the instrument to come up, I can see salmon jumping, that's amazing.
This issue of ocean acidification that threatens that ability to rely commercially on these resources and also to rely on them recreationally and socially and culturally.
Based on the chemistry of the water and how marine life respond to chemistry, the kinds of organisms that we think are the most vulnerable are the ones that build a shell. So oyster shells, clam shells, and corals.
So when we talk about ocean acidification, what we're talking about is a change in carbonate chemistry of the ocean due to the increase in atmospheric CO2 from fossil fuel combustion, as well as other local processes that change that chemistry. And so the issue comes in is that we're changing that chemistry faster than we have in the last million years in the Earth's history. And that's having predictable consequences on the chemistry as well as consequences on the organisms that we're just starting to understand now.
So we've identified the Oregon coast as one of these early impact systems. So our chemistry is already changing and has changed dramatically.
The waters that reached Oregon's coast, if you stand on the coast and look out and see this great blue expanse, you think, oh, that's just one big bathtub of water. You're not quite sure what's there, where it's coming from. But over the years, we understand very well how that water gets there. And that water reaches Oregon shore from far across the North Pacific, off to the northeast of Japan, actually. When it's at the atmosphere, it gets the oxygen and the CO2 from the atmosphere mixed into it. It's cold enough there that the water gets dense or heavy and it sinks down to beneath the waves to about a couple hundred meters and starts this long journey across the North Pacific. And there are actually two branches. One of them comes across the northern Gulf of Alaska. Another one takes this amazingly convoluted route. Along that path, the oxygen gets lower, the CO2 goes up, the pH goes down, it gets more acidic before it reaches Oregon shores. So if you think about the rising CO2 levels in the atmosphere, the water we're seeing at depth off Oregon has the signature of many decades ago.
Even if we absolutely stop the CO2 emissions today and cap the atmospheric levels, there's still a 30 to 50 year increase we're going to see before that carbon, at least along our coast, works its way out.
We're able to manipulate things here to the best of our abilities, but obviously we cannot manipulate what's going on in the ocean. I think we're just scratching on the surface of this problem. I think, at least in my lifetime, that we'll still be trying to figure it out, and probably long after I'm dead. I think it's going to be something that people are going to struggle with and try to make better.
One other canary in the coal mine is a pteropod. These are very delicate, beautiful, elaborate swimming snails. They are important in their own right as members of zooplankton communities, but they're also a very highly prized food for salmon.
There's some really good work being done now that shows pteropod effects in the environments now without experimental manipulation, that we're seeing the shells of the pteropods actually partially dissolved.
The impacts of having these kinds of changes happen on such a large scale, and in the event that they became catastrophic, are really more than just economic. Clearly it affects my ability to do business here, to sell local fish if the supply is diminished or threatened in that way. And of course, everybody else who's involved in that, the entire fleet that goes and catches, the support services here, the supply stores. There's a whole identity for us here on the coast that are in this industry that we have a lot of pride in, and it's something that would be impossible to replace.
We know that these impacts are happening. What we don't know, and what we need to know, is what's happening to the ecosystem at large. We anticipate and are concerned about impacts to fish. We're concerned about impacts to crustaceans like crab and shrimp, but we need more research. And what we know now is that some of the species that are low on the food chain are being impacted, and that implies that there are ecosystem-wide, food web-wide impacts that we're going to start to see.
We're going to see changes in chemistry that the rest of the ocean won't see for decades and decades. So on the one hand, we're going to be the hardest and first hit. But on the other hand, I think it's important that what we learn today in Oregon's coastal waters, that is invaluable. There's really no substitute for the kinds of information that we're going to gain by understanding our ocean. There's no substitute for that. That was part one of what I wanted to present to you tonight. And part two is really about how do we get to this point? How do we get to this point where we come to think of something that's almost esoteric about changes in carbonate chemistry, really nerdy stuff, as something that we should be worried about? And what's the science behind thinking about ocean acidification as an issue for us? And I'll take you from the very beginning from my perspective as a scientist in Oregon. And when I first got to Oregon State University, we had some early questions from the fishermen, because in 2002, the fishermen, the crabbers in particular, were pulling up crab pots that are full of dead crabs. That's not normal. So they're like, well, what's happening? So there's this mystery, what's killing the crabs? And it turns out the culprit was oxygen. We had a low oxygen problem. This is a dated graph. The black is what it's usually the mean. If you take a water column profile, when I'm out at Newport and I take a sensor and drop it through the water column, the red is what we saw in 2002. So you see that we had a lot lower oxygen than normal. So we were able to identify, I know why there are dead crabs. There's low oxygen in the water. But the problem is, why was it so low? What's different? What's changing? And I'll confess that when I went out to look at this problem, it was literally my first research cruise at OSU. I was a newly minted PhD. We took the Alaka out and then, do some water column measurements. And I thought, this is a classic rookie mistake, right? I looked out, and I've been hearing horror stories about working in the Oregon coast. Like, we're going to just get beaten up. But it was beautiful. It was a glassy, calm day. Not a breeze in sight. The water, it kind of has that oily look to it. It's like, wow. This can't be normal. And I thought, the ocean ran out of oxygen because we didn't have any winds to mix air back into it. And, it was around that time, that there's a movie called The Perfect Storm. And I thought, okay, we have the title for our scientific paper. It's going to be the Perfect Calm. So I thought, okay, we haven't made. But then, of course, a couple of weeks later, the next week, the winds came back. We went back out, expecting the oxygen to be back up high, but it's still low. And at the same time, we had colleagues who were working in a much larger research vessel offshore of us at the continental shelf, and they were seeing low oxygen water. So what we were seeing wasn't this very localized, right near shore, no wind problem. So why was it so low? It turns out, when we think about our coastal ocean, even in the near shore, we actually have to look far away for drivers. And we think about drivers, well, we know winds are important, right? Because that's the engine that's driving out upwelling currents. But what's upwelling bringing up? Upwelling is bringing up water that's high in nutrients. That's why we have such a productive coast. But it's also bringing up waters that are naturally low in oxygen and also high in CO2, which I'll get to halfway through my talk. So there's a conduit, there's a pipe. Upwelling brings this low oxygen water up to our shore. And it turns out in 2002, this water was lower in oxygen to begin with. So we had this kind of anomalous event. Somehow in the North Pacific, it was feeding us lower oxygen water than we should have been getting. And the conclusion of my first foray into marine science in Oregon was that, well, wow, that was a once-in-a-lifetime event. The perfect calm, well, it wasn't perfect calm, it turned out, but it was a once-in-a-lifetime low-oxygen event because people had not heard about it. The fishermen said, hey, this isn't normal. And we thought, well, maybe it's a local Oregon, if not Central Oregon, problem. That was kind of my take-home from that first year of research. But in 2006, we were out with biologists from Oregon Department of Fish and Wildlife, and this is what a Cape Perpetual Reef, this is actually another marine reserve south of us. This is what the Perpetual Reef looks like normally. But this is what we found when they deployed their robotic submarine to the seafloor. So these are dead Dungeness crabs, crab parts, and that's a dead sea star, one of the sunflower stars that's already rotting away. So that's not normal either. So what we thought was a once-in-a-lifetime event, well, it came back again. And when we took our data, it turns out it's not such a one-time event after all. This is, I'll orient you. I call this a martini plot. So this is, the red dot is the amount of, the lowest oxygen value that we saw. If it's very, very small, it means we almost had zero. If the red dot is outside that green envelope, it means that it was above what we call hypoxia threshold. As you can see, over a decade of measurement on the Oregon Shelf, every single year we see low oxygen waters that are considered hypoxic somewhere along our shelf. So, this is actually not a one-off thing. And it turns out it's not very local either. We've been collaborating with oceanographers from NOAA, and they do this amazing coast-wide survey for groundfish, right? And if you look at this, this is the west coast of North America. The hot colors, the reds, are low oxygen. And you can see that even though we were working just over here, the waters that we've been sampling was just one patch, just one slice of a ribbon of low oxygen water that runs up and down the coast. So it's not a one-time event, it's not a local Oregon problem. And over time, we've come to realize that, well, remember upwelling, that's winds, and remember the source water, that deep water, those are two knobs that climate can turn to really change the kinds of waters that we get along the Oregon coast. So this is about 2006, and we're just kind of wrapping our heads around, okay, low oxygen can be too low in the Oregon coast. This is not normal, and this is something that might be accentuated by climate change. But right at the same time, this article came out in Scientific American, The Dangers of Ocean Acidification. And this was kind of a watershed article because before 2006, you could probably, the people who knew about ocean acidification could probably fit in this room, the scientists who were working on this. But once this article came out, it really put this issue on the top of the research agenda for a lot of marine scientists. And it's by a scientist named Scott Doney, who's fantastic researchers. So what do we mean by ocean acidification? So this is how I walk through it, is that, the ocean has been just providing us a tremendous service. Carbon dioxide dissolves in seawater, so it's absorbing CO2. And it's actually, the ocean has absorbed about a quarter of our carbon emissions, which is great. What a fantastic service it is doing. And, we're, of course, increasing the amount of CO2 we have in the atmosphere. I have a sixth grader, so he's a 380 kid. So when my son was born, atmospheric CO2 was 380. I'm a 335 guy. So you can actually trace, what's your birth year CO2. So we've been changing this number globally. And what's the consequence of that? Well, so this is usually the part where I'll give you a gratuitous chemistry lesson. We get to talk about carbon speciation, but just think about it this way, that when we have more CO2 in the atmosphere, well, more of it goes into the ocean. When that CO2 goes into the ocean, it's touchy on things like PCO2, partial pressure of CO2, pH you might have heard of or remember from high school. And here's a funny one, this omega symbol. It's saturation state. And it almost seems like, yeah, this is what I knew it. Scientists would make something really complicated, have a Greek symbol for something that, it's hard to explain. But I'm going to return to this Greek symbol, saturation state, in a bit. So, good news, ocean has been absorbing CO2. Bad news, it absorbs so much CO2 that it's measurably changed ocean chemistry. And if you go to the coast of the Pacific Ocean near Hawaii, where they've been able to measure high quality water chemistry for a couple of decades, you see that we've been increasing the partial pressure of CO2 in seawater, and we've been dropping pH. So that's measurable. Thumbs down. Thumbs down is that the ocean is now acidifying at the fastest rate that we've seen in 300 million years. We're really pouring it on. Thumbs down is that marine life are being impacted today already. So we saw the example of the pteropod and the oyster industry. And bigger changes are yet to come. So we're worried about the cascading ecosystem consequences of fundamentally changing CO2. Now, okay, global change, that's big, but yeah, we've got lots of problems, right? Isn't ocean acidification one of these, bucket list problems? So that when my son, when he retires, and he wants to go on that once-in-a-lifetime scuba diving trip, to see the reefs of Vanuatu, he's not going to have as fulfilling a time because the reefs, in this far-off exotic place isn't going to be as nice as it is today. So that's, yeah, it's a problem, but, that's somebody else's bucket list problem. Actually, don't think about the reefs of Vanuatu when you think about where ocean acidification is impacting. It's our coast. So think about the hardworking coastal systems of our state. When you think of, what are the hot spots of places that are being impacted by CO2 in the ocean? And why is that? Why are we so vulnerable? Well, there's two sides of it, right? Is that you look at the kinds of things that make up the biodiversity of our coast, a lot of things build shells. So, you have these urchins, there's coralline algae, you have mussels, and the things that build these carbonate shells, they're really, really sensitive to changes in carbonate chemistry, CO2 chemistry. So that symbol I talked about, omega, that actually describes whether a shell is likely to grow or dissolve. So we have waters that we can actually dissolve seashells in now. So that's the biology. We've got a lot of things that build a shell, so they care about water chemistry. And the other is that, so this is a figure, a model projection from looking at the tropical ocean, and this is that funny Greek symbol, omega, saturation state. And this is atmospheric CO2. So we're at about here, we're just north of 400 ppm. And this is saying, well, as we add more and more CO2 in the atmosphere, how will water chemistry change in the ocean? And you said, wow, tropical ocean, they're taking a dive, but boy, they don't hit one, not for at least 7,500 years. So, long ways away. The red, that's us, California current. So it's telling us that in the bottom waters, we are already at that point where we can actually dissolve seashell. I can take shells from the beach. I can replicate the water chemistry that we have today, and I can measure the dissolution of things. So we're already there in the saturation state, and it's only going to get worse and worse in really the near future. So again, don't think of it as a far-off bucket list problem. This is something that we will see. And you guys how many of you have heard about the Whiskey Creek problem? So, I think, that's one of these amazing examples of ocean acidification, this global problem hitting home. But I've also heard people say, well, okay, ocean acidification, that's just a problem for oyster lovers. And to be honest, my wife, she really couldn't care less about an oyster. My side of the family, we love it. My wife's family, they're from Minnesota. Fresh seafood usually means a frozen block of cod, so they're really not that into seafood. But as we accumulate science, as we do more and more research, we're seeing that they're actually literally every single day, we find out a new species that has been evaluated for sensitivity to ocean acidification. So the list grows, everything from the base of the food web, so the green stuff, to the grazers, to the shrimp, to Dungeness crab. We've added Dungeness crab to the list, to fishes. So now it's like we're starting to impact things that really have much broader consequences for our coastal economies. Now I'm going to. Now I started off my talk talking about dissolved oxygen, hypoxia. Why am I talking about these two things together? Am I just kind of piling it on? Well, this is what I do. This is my day job. I go to sea and I throw out instruments into the ocean and just pray that one, they worked, and two, that I get them back. And when that happens over the course of a summer, this is what I get. So this is April through end of September. This is partial pressure of CO2. So we see that it's a lot of variability. And whenever it's high, that's when the winds are blowing from the north. So we're getting up on the currents. So, and when we have numbers that are north of 800, that's when we can actually dissolve a shell. So this is a pteropod shell. This is a pteropod shell after it's been exposed to high CO2 water. So that's the CO2 picture. This is the dissolved oxygen picture. So they're actually two sides of the same coin. So whenever we have high CO2, we have low oxygen. So they're just mirror images of each other. So that on the one hand, you can't grow a shell from ocean acidification, and on the flip side, with hypoxia, you don't have enough oxygen, you can't breathe, and you actually can suffocate fishes. And this is right off Cape Perpetua. This is about a mile from the beach. That's where we have our mooring. And this is, they have this this mirror image because, one, I told you that the water that we upwell to our coast, it comes from deep down in the ocean, and that water is naturally low in oxygen. Well, why is it low? It's because it's taken that 5-decade journey across the ocean, and it had not seen a breath of air over that time. So in 5 decades, all of these microbes have been using up the oxygen. And when they use up oxygen, they also give off CO2, just as we are doing today. They've just been respiring. It's not their fault. That's just biogeochemistry. Now, this poses a challenge for us, right? Can we get ahead of the curve on ocean changes, such as ocean acidification, hypoxia? And really, the question to us is, can we translate new ocean science to new ocean policies? Can we take what we are learning really within the time span of a decade, real big challenges, and turn that into things that will put us in a better position to confront the future? Well, I'll talk about one example. There's starting in 2013, there was a panel put together by Oregon, California, Washington, and BC. So these states and the province convened a panel of scientists to really try to get at a harder problem, to give decision makers some guidance. Is this a big deal? If it is, what should they be doing about it? And I served as a co-chair of this panel. Well, what do we find? And I'll just give you some. You can go to the website and download the report. As far as a report from 20 scientists go, it's actually pretty readable. It's not like a giant phone book of appendices. But I'll just break it down to the key messages. On the one hand, I think when we were starting the panel, one of the views that we heard a lot was that, well, ocean acidification and hypoxia, these are global problems. It's something that we have. There's nothing that we as individual states, let alone individuals, can do anything about. So OA and hypoxia is something that we wait and let happen to us. Now, as a scientific community, what we can do is just watch it. We can measure that decline really precisely, and we'll get better and better at it over time. But we said, no, that's not the way to think about this. It's actually that we should think about it is that OA and hypoxia, there are things that we can do and we should do to get out in front of these problems. What do we mean by that? This is breaking down further the panel's finding. It's just this is the roadmap ahead. So yes, we need to do something about carbon emissions, but that doesn't mean that we get to sit back and wait until that global problem takes care of itself. Instead, there are really two flavors of local actions. So things that we can do as citizens, municipalities, states, regional governments, and nations. One is that we can reduce exposure, and the other is that we can enhance the ability of biota to cope. What do we mean by that? So reducing exposure is that we want to reduce the local nutrient and carbon inputs that exacerbates the problem, right? On the other hand, we can also enhance the ability of biota to cope. What do we mean by that? Well, reduce other stressors. If we're facing a big stress, let's not make it any worse by increasing local stressors. And the other part is advanced adaptive capacity. So this is about, can we enhance the ability of ecosystems, populations, to resist the changes ahead, or to rebound from the changes ahead. And we offer that, well, you wanted to invest in research and monitoring to make sure that we have answers. So, we have to admit that this is kind of the trajectory we've been on, right? Is that when you think about, well, what should you do about ocean acidification and hypoxia? Well, wait till we discover cold fusion and then that solves the problem. No, we're saying that think about the local things that we can do to really buy us time. But it's still unsatisfying because there aren't a lot of tools in that toolbox, right? And it feels like we're in this low information diet, so that over time, yeah, we're going to get more and more solutions, but boy, that's not a steep slope. And what we really want is to jump track. We want to go from this low information diet to a high information diet so that we can develop more and more solutions over time. And what would that get us? Well, we think that we want to have smarter detection and monitoring because we want to know what's ahead, where we're heading. We want to know where we can reduce local stressors where they are important. And this is really important because my colleagues on the panel who were working in California, well, they were representing a state. For example, in Southern California, they have nearly 10 billion people flushing their toilets in the Southern California Bight. And they were ready, their discharges were ready to say, if we're going to need to spend $1 billion to solve this problem so that they do not exacerbate the problem, they will do it. But here, we're actually in a region of the world where, I think we're ahead of the curve on this one. Another example we can do to, get us to a high efficient diet, why that's important, is that we want to enlist and develop tools to support resilience. So that's that ability to bounce back or resist the changes ahead. Now, at this point, you should say, wait a second, the last two slides, you just told us that we need more research and monitoring. So you should always be suspicious of a scientist when they say more research and monitoring is needed. Because, don't we have a lot? If you go on to the Global Ocean Acidification Observing Network website, this is what shows up. Like, wow, you guys have a lot of stuff in the water. You're measuring chemistry everywhere. And let's zoom in a little bit to the West Coast, which is really the leader in a lot of this research. And it's like, yeah, we've got lots of assets out there, keeping an eye on the ocean and giving us information that can be translated into solutions. Well, let's zero in further just to our state in Northern California, and we'll take out the ship measurements because there's a lot of just kind of one-time ship passing. They're not really good for monitoring because it's just a one-off. It's like, well, that's not so bad. But let's remove stations that are no longer active because it turns out there's a lot of those stations are just kind of one time where we've made a measurement. And let's take out the ones that are not in state waters. So, and the picture that we get is pretty different, right? So that if I want to know something between Bodega Bay and Newport, I've got to do a lot of guessing to know what conditions are between. And truth be told, I could just put in sea monsters in between because I have no idea what Northern California looks like, let alone Port Orford, right? So we have the sea monster problem with information about ocean acidification. So how can we fix this sea monster problem? And two, how can we foster a more resilient coastal ecosystem? More resilient, not resilience. Well, this is one of the prime candidate, our Oregon's system of marine reserves, right? Because when we think about marine reserves, well, what are they doing? Well, one is that they're really refuges where other stressors are minimized, right? Because you don't get to, have a lot of activities there. There's no development. Two, they're reservoirs of demographic and genetic diversity that underlie resilience. So genetic diversity, that's kind of easy to think about, right? Because, you have a pretty deep gene pool, so that chances are you're going to have some individual in the population that has that, ability to do a little better in a high CO2 world. So we want to make sure that we preserve that. The other is demographic diversity. So as biologists, what makes a population really unresilient? So it'll be having every single fish exactly the same age. And a lot of exploited fish populations are kind of like that, right? Every single fish is the same age. But in reserves, we get to broaden that age class. So we have fishes that are 1-year-old, 2-year-old, 10-year-old, 20, and hopefully 50 years old. So that's good. Third is that marine reserves, they can serve as natural listening posts to detect and understand ocean changes. Because these are the few legacy places where we get to study and monitor the ocean in the absence of local human impacts. And the other thing about marine reserves is that we can take advantage of just the tremendous energy that's around these special sites. So to find out where we have both hotspots and potential refuges from ocean acidification, I have a project where I work with representatives up and down the coast that center around marine reserves, where we actually install these pH sensors, and this is one right here. It's actually, this one's marked Cascade Head. I was hoping Dick Vanderschaft was going to be here so I could hand it off to him. But when we're able to install these sensors, and we get this really fine-grained picture of the coast. So instead of thinking about the ocean as, well, there's a 1-2 knot current in the summer, how can there be any geography to chemistry levels? In fact, we see that there's actually a lot of neighborhoods, right? We see this is the Cape Perpetua region, real hot spot for exposure. A little less to the north. And then this is this is Redfish Rock. It's one of the sites that we have some of the best water with respect to having a moderated pH value. And now we know that. And the other thing about marine reserves is that, what I found is that they're really a nexus for people to get engaged in marine science and in communicating the ocean changes. So these are a couple of things, Surfrider and the Marine Reserve program. We're able to talk about what's going on with ocean acidification in our state. So I had this challenge, like, well, can we translate new ocean science, so this kind of nerdy stuff that I do, into new ocean policy? And actually the message is yes. In California, last September, they passed 2 bills that essentially establishes a task force to access the best available science. So science has a seat at the table when California is making decisions. Implement climate change adaptation in the ocean, develop CO2 mitigation through seagrass beds. They're actually trying to redo water quality criteria to reflect ocean acidification and hypoxia, inventory and monitor OH vulnerability. So all these things are happening, and they're putting money behind this. They threw $3.4 million behind these initiatives last fall. And in Oregon, we've had a number of really forward-thinking ocean legislation that have been passed. The Ocean Science Trust, the Shellfish Policy, there's a ocean-going research vessel program. And there's this, Senate Bill 1039. It's in Salem right now. It's working its way through. And it's sponsored by Senators Roblin and Cruz. And I'm a geek. And this seems to be a bill for an act relating to ocean chemistry. So, our decision makers, our elected officials, they get it. And they're trying to position our state in a way so that we're not behind the curve on this issue. So this is very forward thinking. And I have to say that, as a scientist, I do my stuff, And do people care? Am I reaching people? Do people that make decisions actually listen and value science? This was a couple of weeks ago at the Hatfield Marine Science Center. This is Congressman Bonamici. This is the second time I've had a meeting with her where she wanted to find out about the advances in science so that she can take that knowledge and translate that to new actions at a federal level. So and that really keeps us going, that people care and listen. So I'll wrap up by saying, I think these are some take-home points. It's hard to read, but one is that think about state waters as the front lines for local actions for addressing this global ocean challenge. Two is that, ocean acidification, blind ocean management and policies are really behind us. Remember, 2006, pre-2006, we didn't even think about it. Now, policies that are cognizant and aware and addresses OA, that's the forward, that's the future. And new ocean science can translate into new ocean policy. And the last, it's really important one to me, is that Oregon is leading the way as we tap into local partnerships and scientific expertise to really get ahead of the curve on this. And I should say that, part of that $3.4 million that California allocated is to replicate the citizen science network that we developed, pioneered in Oregon, to use marine reserves as the listening post for ocean asphyxia. I'll end with this video, again, from my colleagues at ODF&W, that really shows, we have an amazing ocean out there. This is fantastic. This is like going diving in a coral reef. When I see fish population like that, this is what, to me, resilience means. What does it mean to have a resilient ecosystem? It's that we preserve this stuff, right? And in just a second, and we preserve that spawning stock biomass because we get stuff like this. So this is young of the year rockfish recruiting to a nearshore reef. It's hard to see, but all the things darting like mice, those are young of the year rockfish. So that's the future that we have to look forward to if we do well stewarding our coastal oceans. Thank you.